Our last section in this chapter deals with graphing rational functions, sections 2.6 and 2.7. To begin, let's review some of the things you looked at last year in math when it comes to rational functions. First of all, a rational function is any function that's going to have x's in the denominator. So y equals 1 over x plus 2 would be an example. So y equals 1 over x plus 2 is something that could be rational. So the domain of a rational function is from negative infinity to infinity. That's a false statement because you have to exclude, when you've got an x in the denominator, the fact that x cannot equal 0. Or in the case up here, I've got a plus 2 in the denominator, x can't equal a negative 2. So it can't be negative infinity to infinity. Second, the reciprocal function is symmetric around the y-axis, thus is an even function. Well, if you look at the reciprocal function, that's y equals 1 over x. And that's symmetric around the origin, so it's an odd function. The third thing, vertical asymptotes are found when a factor cancels out. That's false. Reason is because wholes occur when factors cancel out. Vertical asymptotes occur when the factors do not cancel out. Horizontal asymptotes occur at y equals 0 when the degree of the numerator is larger than the degree of the denominator. Well, once again, that's a false statement, because a horizontal asymptote will occur if we've got x cubed plus a bunch of other stuff over x to the fourth plus a bunch of other stuff, when the degree of the denominator is the one that's larger. A hole can occur when there is no horizontal asymptote. That is true, but it doesn't have to always be the case, but realize that it can happen. A function can have two horizontal asymptotes. That's a true statement when we've got absolute values in the denominator. You end up with a plus and minus version, so you get two different asymptotes that are horizontal. A function cannot cross a vertical or a horizontal asymptote. That's a false statement. A function cannot cross a vertical asymptote. That's absolutely true. But the horizontal asymptote is just a boundary line of where the graph goes as we get extremely large. So there are some times that it will fluctuate back and forth around a horizontal asymptote. And then finally, a new term for you. A slant asymptote occurs when the degree of the numerator is exactly 1 more than the degree of the denominator, and that's a true statement, something we'll be looking at in this unit. So there's a brief review just in true-false statement. Now, summarizing all that down here in some terms, a vertical asymptote occurs when there is a 0 in the denominator and factors do not cancel. So if I had something like x plus 3 over x minus 2, that vertical asymptote would occur at x is equal to 2 because that x minus 2 does not cancel out. Holes occur when there is a 0 in the denominator and the factors do cancel. So going along that same thought process, if I had x plus 3 over x plus 3, I know x cannot equal a negative 3 because of that 0 in the denominator. But since those two factors cancel out, I am going to end up with a hole as opposed to an asymptote. The third idea, a horizontal asymptote, occurs when the degree of the numerator is equal to or smaller than the degree of the denominator. So if we look at that, if I had x to the fourth plus x cubed plus 9x squared and all this other stuff over 7x to the fourth plus 9x cubed minus 12x squared and all this other stuff, when I have something that is identical, this is the equal to part, the degrees are both x to the fourth, the coefficients give me my horizontal asymptote. So my horizontal asymptote is going to be y equals 1/7. It's the ratio of the numbers that are in front. If I have something like x to the 4th plus x cubed minus 9x squared over x to the 6th plus 9x to the 4th minus 6, well, now I got x to the 4th over x to the 6th when I look at my largest degrees comparing the numerator to the denominator, and that's going to give me a y equals 0. The last example, if I have a numerator that's larger, this is where you get no horizontal asymptote. So x to the 7th over x to the 4th, that one would not be a horizontal asymptote. And then finally, a slant asymptote is found by using long division when the degree of the numerator is exactly one more than the degree of the denominator. So something like x squared minus x over x plus 1. Since the numerator degree is exactly one more than the denominator, this is going to produce a slant asymptote. And the way you solve for the slant asymptote is you do long division. So x squared minus x divided by x plus 1. If I do long division, what times x gives me x squared? Well, that's x. X squared minus x. Switch the signs. That should be minus when I switch the signs. Gives me a minus 2x plus 0. What times x gives me a negative 2x? Well, that's a minus 2. So minus 2x minus 2. Switch the signs of both. Give me a remainder of 2. The slant asymptote is this piece. It is the quotient excluding the remainder. So in this case, y equals x minus 2 is our slant asymptote. You only take the quotient and you do not include the remainder. The final thing there that we see on this page is just listing the steps in order to graph a rational function. You factor, you find holes and asymptotes, horizontal asymptotes, slant asymptotes, plot the information you know, choose points on each side of the holes or asymptotes, then connect the dots along the asymptotes. So that's nothing new that you haven't seen before when it comes to graphing rational functions. There's just the steps listed out for you. Remember, you don't have to follow every single step in order. You just have to get the information and then plot all your details out.